So our second speaker in this afternoon session is Zawadowski, and we'll talk about duality for positive opetopes and field complex. Thank you, Marek.
Okay, thank you very much. So I'm not going to be very original, thanking organizers of this very nice conference. And even if I'm sorry not to be there in place, I certainly enjoy participating in that conference. So thank you very, very much. And now I go to the subject. That is, I'm going to talk about duality for positive opetopes and three complexes. So, first about a word about opetopes. They came from John Baez and James Tolan, and they seem to be reasonable shapes to serve as a base for the notion of virtual weak omega dimensional category. So that the first notion of that kind was made through the opetopes. They are, for example, particularly good if you want to consider unbiased composition of dimensions of all of cells of all dimensions. In this talk, I will talk sometimes about opetopes, sometimes about positive opetopes. That all opetopes for me are positive. I will explain in a minute what it is. And still a word about dualities. Well, I mean, probably I don't need to say much after what May said 2 days ago. They are, of course, nice mathematical statements. They are useful, and the kind of duality I'm going to talk today is kind of a small duality. It's for the category of shapes. So it can be compared with a duality, for example, for simplicial category delta, which is dual to the category of finite intervals, and another similar duality is for category theta of Joyal, and which is dual to the category of disk of Joyal. So this will be about such dualities, and now there won't be much time to describe all the combinatorics of opetopes. So I will start to introducing opetopes through pictures. And there are two ways to do this. Right? There is one way, basically following Baez and Dolan, original idea, and the other is following Koch, Joel, Bataillon, and Mascari, which is somehow very different. So it starts at the level 0 with 0 opetopes in both conventions are points. And then there is only one opetope, and this can be described as just one arrow like this, or as a mysterious thing like that, which I will explain in a moment. So to get to, okay. So to get a more idea what it is, the opetope starts being interesting from the level 2. So two opetopes have several one cells in the domain and one in the codomain. Opetopes, opetope means that you have one thing in the domain and something in the codomain and something in the domain. Something means at least one thing, but maybe more. In particular, I exclude such empty domain opetopes. They complicate the picture. It's not more difficult to treat them, but it is more complicated, I would say. So such a two opetopes corresponds to such three things, which are so-called constellation trees, which this is, you can look at it as a tree where leaves are dots and circles are internal elements, and there's also one circle at the end, which is a root of the tree. I will explain in a moment what they are. And this is another thing of dimension 3. So you will see that these dots on the right side, they form a tree, and then the circles, they surround some convex subjects. So I will make it precise in a moment. But this is to just give you a little idea what opetopes are in both things. So, and you know, just to tell you what is the point of this talk is that these opetopes live on the left, lived for like more than 20 years, and then on the right, it's like 15 years or so. And it was clear how to pass from one convention to the other, but it was never made into a functor. And this talk is essentially to explain you what kind of morpheus you can impose on this, what I call here tree complexes, to get a dual category to the category of opetopes and some morpheus, not all the morpheus, but some degeneracy morpheus, no phases. So in the remainder of the talk, I want to define precisely what is the category of tree complexes and the category of opetopes. This is maybe less explicitly. And then explain, state duality theorem, maybe think about the construction, how to pass from one to the other. And then at the end, I will a little bit speculate what can be done more about this. Okay, so let me start with the definition of a tree for this talk. It's a finite poset with binary sums and no ints of subsets which are not linearly ordered. So there are ints, but only those that must be there, no other ints. So it sort of fits the idea of a tree, I think, one of the ideas. Right? So in particular, the tree can be empty, but if it's not empty, it has a largest element, which is a root. And the tree embeddings are the one-to-one function that preserves and reflects on. So then in the trees, you can consider convex subtrees, and this is what you imagine it should be, that if these are subsets with the largest element, definitely the convex subset must be non-empty, has to have largest element, and whenever you have two elements in this subset and there is something in between, then it also has to belong to the subset. Right? So this is a typical convexity property. And then for every tree T, I will consider the set of the convex subset of the tree, and this will be ST of. Okay, and then there is a notion of constellation. Constellation trees we already seen on the first slide on the right. And so the formal definition is as follows. Constellation is a triple where we have two trees, S1 and S2, and a monotone function sigma that satisfies two conditions, namely it preserves top elements if this top element exists, because S1 can be empty, but if this top element exists, it will be sent to the top element of ST or S0. And if we have two elements in S1 and a constellation morphism will send them for two subtrees, convex subtrees that are not disjoint, then already these elements must be comparable one way or another. And basically this condition means that we can write these nice pictures with circles that do not cross one another, and this is definitely what we want. Then once we have the constellations, then we can consider constellation trees, and these are trees made from S1. We add to S1 S0 as leaves over elements of S1, and over which element of S is a leaf. So this is the condition that S0 lives as a leaf over S1 if S0 belongs to sigma of S1. So you just put one, decorate one, one partial order S0 with leaves of S1 with leaves from S0. So this is a notion of constellation. There is probably the most important definition in the whole talk, namely the Morpheus of constellations. So if you have two constellations and then we have two monotone function between trees, then this monotone function induce a monotone function between constellation trees, right? And this is a kind of a trivial observation, cannot be anything else than that. But it might happen that this function preserves binary subs, and if it preserves binary subs in addition to being monotone function, then we say that this pair of morpheus F1 and F0 is a morpheus of constellations. And now I can define the category of three complexes, namely the objects. This is essentially the simplification of the idea of Bourgeois, Battaglia, and Mascari, is that it's a sequence of trees together with constellations. That is, we have a sequence of functions for every natural number I. We have a constellation from T I plus 1 to, well, we have a constellation map from T I plus 1 to ST of T I. This is a part of the definition. Still, to have a tree complex, we insist that T0 is a singleton, and almost all sets must be empty. That is, from certain moment on, all the sets must be empty because we are just talking about finite structures. And then also we insist that the last one is also singleton. So that's the category of three complexes. And then now okay, so still I have to explain what are the morphics of three complexes. And these are, in this situation, I think that they are more or less obvious now. Because if we have three complexes, and the morpheus of three complexes is a family of monotone function, so that if we take this morpheus just one next to the other, they become the morpheus of corresponding constellation trees. So they preserve binary subs. This is something. If you try to unravel this definition, it takes a moment, but the very definition is pretty simple. So in that way, we have a category of three complexes. Now I will move for a moment to opetopes. And here, first of all, if I will define the positive, opetopic cardinal. And for this, I need to tell you what are the primitive notions concerning this picture. And essentially two things that we have. We have the operation of taking a codomain. This is for every cell, say A. We have an operation of taking a codomain of A. This is in this case X0. This is like here. And there is an operation of taking the domain of cell. And in that case, it is you associate to an element, a whole set of faces of dimension 1. And in this case, on this picture, it would be like this. And these are primitive notions. Then there are also two derived notions. There are two orders. At the moment, it will be just binary relations, but the axiom will say that they must be strict orders. So there is upper one and lower. The lower one will tell you that X x3 is smaller than x2 because they sort of connect through the lower cell. The codomain of x3 is in the domain of x2, and this is why x3 is in the sense of lower order smaller than x2. But then you can pass from one cell to the other with the cell of the higher dimension. So for example, from x2 to x0, you can pass through A1. So x0 is a codomain of an A1, and x2 is in the domain of it. That's why x2 will be considered as smaller than x2 in the sense of upper order. And then there are axioms that tell you what is an opetopic cardinal. So this is an infinite family of sets. They are almost all empty, and there are maps delta and gamma from sk to sk minus 1. So the face of dimension 1. Gamma is a function, delta is a function to the non-empty subsets, and also derived with upper and lower orders, and we have 4 conditions. Globularity is something that you should probably look on your own, because this is something obvious if you look at the pictures. But you need such a condition, then we want to say that this upper order is a strict order, and on 0 cell it's even linear order just for connectivity. This order should be disjoint, and you have pencil linearity, which is better explained at a picture, meaning that if you take faces with a common codomain, they should be linearly ordered by upper order, and if you have faces with something common in the domain, they also should be ordered by upper order. And that's a definition of a cardinal. And if you have opetopic cardinal, there is a way to cut it down to have just positive opetopes. Basically, you should say that if you look from the front, you should see only one face in the set. And for this, there is a notion of size. I'm not going to go to the details, but this is just a little addition to what we've seen, and you can believe me that such thing will be cut out on such a right. Okay, and that's the notion of positive opetopes. And now for the Morpheus. So in the category of opetopes, usually you consider Morpheus that are embedding phase into the whole opetop. And this is what is called category of P-op, so of positive opetop with phases. But such a category can be easily using opetopic cardinals embedded into strict omega categories. And this embedding is full on isomorphism, meaning that basically you can borrow to category of opetops Morpheus from omega categories. So you can think that Morpheus between opetops is an omega functor. And if the phase functor is just such an omega functor between opetops that sends generators to generators, right? In the sense that these opetops considered as omega categories are polygraphs, so they are built from generators, and phases send generators to generators. And contraction maps that I am mostly interested in here are such that send generators to either generators or to identities on generators of lower dimension. And that's a notion which is important for our duality. And now we have a statement saying that positive opetopes with epicontractions from a dual category to the category of 3 complexes with the maps as I described. And that's the duality theorem. maybe since I have, I guess, like 2 or 3 minutes, right? I will say something about how we pass at least from opetopes to 3 complexes, namely to define partial order for 3 complexes. Each partial order is just a set of faces in the opetopes that are not codomains of faces of higher dimension, so pi minus gamma of pi plus 1, with the lower order. And these are the partial orders. And then constellation maps are defined through upper order, namely for a face in pi plus 1 star, or the set of the cells that the cells in the pi of p will be those cells that are smaller in the upper sense than gamma of p. Again, I wish I had more time to draw nice pictures, but I don't. So at this, for morphism, essentially what we do if we have a yaw-type morphism of opetopes is that we sort of define such maps that well, here is the definition. I'm not going probably to get into this definition. It is a simple observation, but maybe I don't have enough time to explain it in detail. So in that direction, the definition is what you see, and it's pretty simple, but the other way around, it's a little bit more complicated. And that's the story of the duality. And now a little bit about speculations. Namely, what I described to you is a duality between opetopes with epicontractions and as dual to the category of 3 complexes defined by Cogel, Bataille, and Pascaria. And this is, yeah. And then one can easily extend this duality to duality that will work for opetopic cardinals, but still with contraction and epimorphism. And this category contains the category of, I would say, globular cardinal with epimorphism. So it's a part of the theta category of Joyal, which is dual to the category of planar trees and corresponding morphism. This category is, this duality contains in itself duality for delta and for finite linear orders, right? And finite intervals, but only with epis and monos. And this is just to connect to maybe the world where May Gerke is living. It is dual to the poset with finite poset with epimorphism, which is dual to distributive lattice with monomorph. And if you look at this slide, then you see that this part is sort of just restricting something that we know and like. Namely, you can extend it because on that part you don't need to say epi, and in the lower part you don't need to say mono. But we have a duality for finite poset and finite distributive lattice, for delta and finite intervals, and for Joel's theta category and Joel's disks. But then if you want to go to this side, this is not clear what to put here and what to put here. That is how to sort of impose these dummy nodes. Okay, and
we are running out of time.
Yes, so this is a kind of a papers relevant to the talk. What is in the talk is in the last one, so you can look it up in archives. Thank you.
Thank you. time for a short question, if any. What about online? No. So thank you, Marek. And thank you.